Përshëndetje, unë jam Fationa Nefeli Halilaj dhe me Dario Dollani kemi kryer projektin për radhë aktivitetit të metaleve në lëndën e kimisë. Metalet, më shumë se 90% e elementeve kimike janë metale. Disa nga metalet njeriu ka njohur që në kohë të lashta duke u njohur me vetitë e hekurit, nikelit, kromit, bakrit. Metalet më së shpeshti i hasim në korën e tokës, por ato në përqindje të vogël i hasim edhe të organizmat e gjallë, të cilët ndihmojnë për kryerjen e proceseve jetësore. Rusia zotëron 20% të rezervave ekzistuese në botë të metaleve të rrallë toksor, por nxjerrjen e tyre nuk i tekalon 2% e prodhimit të tyre botëror. Mërkuri është metali i vetëm lëng në kushte normale. Metalet mund të punohen ose lakohen pa u kaputur. Metalet rrihen nga magneti, me anë të tij ndahet hekuri. Sistemi periodik ndahet në 3 pjesë: metalet, jo metalet. Vititë e metaleve janë të ngurtë përveç mërkurit, janë përcjellës të mirë të elektricitetsisë, kanë pikë relativisht të larta shkrirje, janë kullues, kanë aftësi që t'japin elektrone duke formuar ione pozitive, kanë shkëlqim metalik dhe kanë fortësi të madhe dhe qëndrueshmëri të tyre. Këto ishin dhe vetitë e metaleve. Rradha e aktivitetit të metalit. Rradha e aktivitetit të metaleve bazohet në prirjen për të dhënë elektronin. Disa metale kanë prirjen më të lartë e disa metale kanë prirjen më të ulët. Metalet me prirjen më të lartë janë më aktiv. Metalet me prirjen më të ulët janë më pak aktiv. Metalet më aktiv janë metalet alkalin të grupit të parë. Ata janë më aktiv sepse në shtresën e jashtme kanë vetëm një elektron dhe mund të lëshojnë shumë më kolluaj se metalet e tjera. Atëherë, mbani mend këto gjëra. Rradha e aktivitetit është një listë ku metalet janë renditura në bazë të prirjes të tyre për të dhënë elektrone dhe për të formuar ione pozitive me shtesë elektronike të jashtme të qëndrueshme. Sa më fort jetë kjo prirje, aq më aktiv është metali. Një metal aktiv zëvendëson një metal më pak aktiv nga oksidi dhe tretësira ujore e kripës së tij. Sa më aktiv jetë metali, aq më qëndrueshme janë përbërjet e tij. Ato nuk shpërbëhen lehtë. Sa më aktiv të jetë metali, aq më vështirë keni për të nxjerrë nga mineralet e tij, sepse ato janë përbërje të qëndrueshme. Për nxjerrjen e metaleve më aktive përdoret elektroliza, e cila është një metodë e fuqishme. Sa më pak aktivitet çaj, aq më që dobët e shpirja për të formuar. Radhën e aktivitetit të metaleve nga poshtë vijnë më pak aktiv dhe më lart vijnë më shumë aktiv. Për shembull, kemi kaliumin, natriumin, kalciumin, magnezin, aluminin, zikun, hekurin, nikelin e të tjerë. Kaliumi mund të zëvendësojë natriumin, por natriumi nuk mund ta zëvendësojë kaliumin, por ai mund të zëvendësojë kalciumin. Pra, sa më poshtë jetë, aq më pak aktiv janë ata. Reaksioni me radhën e aktivitetit. Kujtëm, radha e aktivitetit bazohet në prirjen për të dhënë elektronin. Kemi 2Al plus 3ZNO që barabartë me Al2O3 plus 3Zn. Këtu kemi një zëvendësi metalesh, sepse alumini është më aktiv se sa zinku. Po ashtu dhe në reaksionin e dytë kemi zëvendësi metalesh, ndërsa në reaksionin e tretë jo, sepse FeMgCl2 nuk bëhet, sepse magnezi është më aktiv se hekuri. Do ju tregoj një video ku i shpjegon akoma dhe më mirë këto gjëra që sapo unë përmenda. Le të fillojmë.
So, alkali metals like lithium are very reactive. And then you have like alkaline earth metals like magnesium, then aluminum, and then Fe, zinc, nickel. Hydrogen is like the standard. So on the left side you have the active metals, and on the right side of hydrogen you have the inert metals like copper, silver, platinum, and then finally gold. Gold is the last one. As you can see, the precious metals, or also known as the noble metals, these are chemically inert, like silver, platinum, gold. They're not very reactive. They're pretty stable, and so they're resistant to corrosion. And they're also very expensive too. They're precious metals. To the left of hydrogen, you have the reactive metals. These metals, they participate in chemical reactions. They prefer to stay or form ions, or known as cations, which are positively charged ions. So gold, it wants to stay in its metallic form, but aluminum, it prefers to stay as an ion, like aluminum plus 3. So the active metals on the left, they like to give away their electrons. The non-active metals on the right, they like to keep their electrons. So lithium would be considered the most reactive metal, which is out of the elements that's listed here, is the strongest reducing agent. Reducing agents usually like to give away electrons. Gold is the weakest reducing agent. However, the gold 3+ ion is the strongest oxidizing agent out of the metal cations that are listed here. So, if you compare the gold 3+ ion and the aluminum 3+ ion. The aluminum 3+ ion is a weak oxidizing agent, but Au+3 is a strong oxidizing agent. So now let's apply this information with single replacement reactions. So let's say if we have the reaction between zinc metal and hydrochloric acid. So will this reaction work? Is zinc strong enough to displace hydrogen out of the solution? So zinc is to the right of hydrogen on the activity series. Or if you go to Google Images and you type in activity series, you'll see that zinc is above hydrogen. That means that elemental zinc can displace hydrogen out of the solution, since zinc is more active. In the list I gave you in the last page, as you go to the right, the reactivity increases. So zinc is more reactive than hydrogen. So this reaction can work. So since it can work, let's go ahead and predict the products of the reaction, and let's balance the equation as well. So in a single replacement reaction, zinc is going to displace hydrogen out of the solution, and zinc is going to pair up with the chloride ion. So zinc typically has a +2 charge as a cation, and chloride has a -1 charge. When these two get together, they're going to combine in a 1:2 ratio. There's going to be Zn1Cl2. We don't need to write the 1 down. So that's the product for zinc chloride, ZnCl2. And when hydrogen is displaced out of the solution, it's going to turn into its elemental form, which is hydrogen gas. And hydrogen gas is diatomic, so you got to write it as H2. Now, zinc chloride, is it soluble or insoluble? So you need to know your solubility rules. Chlorides are generally soluble, except when bonded to silver, lead, or mercury. So zinc is not an exception. This is soluble. Hydrogen is a gas, so we can put G. So we have our reaction. The only thing we need to do now is to balance the reaction. In order to balance it, we need to put a 2 in front of HCl because we have 2 hydrogens on the right side. And since at this point it's balanced, we have 2 chlorine atoms on both sides, 1 zinc atom on each side, so everything is good. So that's the balanced reaction. Now, by the way, how can you write the net ionic equation for this particular example? To write the net ionic equation, anything that's in the aqueous phase, you need to separate it into ions. So first, let's write the total ionic equation. It's going to be zinc. Now, HCl, we're going to separate into ions. 2H plus, 2Cl minus, and then zinc chloride, we're going to break that into ions as well. We're going to have zinc 2 plus, 2 chloride ions, and H2 gas. Now, what we need to do is we need to eliminate the spectator ions. These are the ions that are found exactly the same on both sides. So what are the spectator ions? The only spectator ions that I see are the 2 chloride ions. They're exactly the same. Zinc is not a spectator ion because these two are different. On the left we have zinc metal, on the right we have the zinc +2 cation. So we can't cancel those two. So what we have left over is the net ionic equation. Metallic zinc reacts with hydrogen, which is in the aqueous phase, and it turns into, or the zinc part turns into the zinc 2 plus cation, which is also dissolved in water, producing hydrogen gas. And so that's the balanced net ionic equation for this single replacement reaction. Let's try another example. Now, let's say that nickel reacts with iron sulfate. Will this reaction work using the activity series? Yes or no? Feel free to pause the video and think about it. Now, on the activity series, we have zinc, Fe, nickel, and then hydrogen. notice that nickel is less reactive than Fe. Therefore, nickel is not strong enough to displace Fe out of the solution. So because nickel is less reactive, this reaction is not going to work, so we can write no reaction. Now, what about this example? Aluminum metal reacts with copper sulfate. Will this reaction work based on the activity series? What would you say? Now, aluminum is over here. Then we have zinc, iron metal, nickel, and then hydrogen. And below hydrogen is copper. So aluminum is definitely strong enough to displace copper out of the solution. So then the answer is yes, this reaction will work. So feel free to pause the video and predict the products of this reaction, balance the equation, and then write the net ionic equation. So let's go ahead and begin. So aluminum is going to kick out copper out of the solution, and as it does so, aluminum is going to pair up with the sulfate ion. Aluminum is in group 3A of the periodic table, and so therefore aluminum has 3 valence electrons and it likes to form a positive 3 charge. Sulfate is a polyatomic ion that you should commit to memory. If not, you can go to Google Images, type in polyatomic ions, and you can find their charges. So sulfate has a negative 2 charge. So to write the formula for this ionic compound, it's going to be Al2SO43. Whenever you have multiple polyatomic ions within a compound, you need to enclose that polyatomic ion in a parentheses. So it's going to be Al2SO43. That's aluminum sulfate. And the other product will be the metal, copper metal. Now, sulfates are generally soluble, so we can write AQ for aluminum sulfate. So that's how you can find the products for this single replacement reaction. So now let's balance the equation. So notice that we have 3 sulfates on the right side. So let's put a 3 in front of copper sulfate. That means that we now have 3 copper atoms on the left side, so we need a 3 in front of Cu. We have 2 aluminum atoms on the right, so we need a 2 in front of Al. So now the reaction is balanced. The next thing we need to do is write the total ionic equation. So everything that's in the aqueous phase, we're going to separate it into ions. So we have 3 copper 2 plus ions and 3 sulfate ions. On the right side, we have 2 aluminum cations, and we have 3 sulfate ions and 3 copper atoms. Now, which of these ions are the spectrin ions? These are the ions that look exactly the same on both sides, so that's the 3 sulfate ions. So what remains is the net ionic equation. So we have aluminum metal reacting with the copper 2 plus ion, which is in the aqueous phase, and that's going to produce the aluminum 3 plus ion, which is also in the aqueous phase, and also we're going to get 3 copper atoms, which is a solid. And so this is the balanced net ionic equation.